Relativity, the scalar product. The measure of distance between neighboring points xi and xi plus the xi prime is the elementary interval. So we have ds squared equals to dx naught all squared minus in brackets dx1 all squared plus dx2 all squared plus dx3 all squared. Now this is the same as dx naught minus dx1 minus dx2 minus dx3. This can be written as a product of two matrices as shown, as can be seen below. So we can write ds squared equals to dx naught minus dx1 minus dx2 minus dx3 times dx naught dx1 dx2 dx3. So actually this is like a column matrix, this one is a row matrix. Now we have dx naught plus 0 plus 0 plus 0. Now we have the second term as can be written as 0 minus dx1 plus 0 plus 0, 0 plus 0 minus dx2 plus 0, 0 plus 0 plus 0 minus dx3. So actually if you try to eliminate the zeros, it still comes back to this matrix here. Now replace the zeros with consecutive dx variables multiplied by zeros. That gives us dx0 plus 0 times dx1 plus 0 times dx2 plus 0 times dx3. Now for the second row we have 0 times dx0 minus dx1 plus 0 times dx2 plus 0 times dx3. For the third row we have 0 times dx0 plus 0 times dx1 minus dx2 plus 0 times dx3. For the third we have 0 times dx0 plus 0 times dx1 plus 0 times dx2 minus dx3. Obviously the variables can be factored out as a column matrix. Here we can, now we have ds squared equals to, so actually when we try to write as a product of two matrices we have 1 0 0 0 0 minus 1 0 0 0 0 minus 1 0 0 0 0 minus 1, then with dx0 dx1 dx2 dx3, and then here you have dx0 dx1 dx2 dx3 with, now this matrix here can be denoted as GIK. So this is GIK, and then the xi is now the second matrix in the middle there, and then the xk is this last matrix. So that gives us, this permits us to write the interval as ds squared equals to GIK dxi dxk. So we'll call that equation 1. Let's analyze the interval from another point of view. Now again, dx squared is equals to dx0 squared minus dx1 squared dx2 squared plus dx3 squared, which is still the same as dx0 minus dx1 minus dx2 dx2 minus dx3. Now we have dx squared equals to this matrix times this matrix. We've seen that. See that dx0 minus dx1 minus dx2 minus dx3 are contravariant and can be changed to the covariant using the relationships. So we know that to change from contravariant to covariant, we know that dx0 will be dx0 in the covariant, meaning that there's no sign change, and we have minus dx1 equals to dx1 the covariant minus dx2, that's in the contravariant, equals to dx2 in the covariant minus dx3 in the contravariant equals to dx3 in the covariant. So I'm going to have this substituted in the above expression for dx squared. Now substituting in the equation for the interval gives us the s squared equals to dx0 dx1 dx2 dx3 times this other matrix. So in this our column matrix, we have simply replaced all the components that we had there in the contravariant to the with this other substitutes for the covariant. So actually here you have covariant components, while here you have contravariant components. Hence the interval can be written as ds squared equals to dxi dxk. We call that equation 2. So you can actually see that this dxi, you see it is in the covariant, that's why you have the I as a subscript, and then dxk is the other matrix here, which is the row matrix. It is in the contravariant, so you have a superscript there. We call that equation 2. Now if you recall equation 1, that's ds squared equals to what we have here, and ds squared for equals to this, that's equation 2. We know that comparing 1 and 2, it can be seen that dxi equals to gik dxi, because equation 1 must be equal to equation 2. So when you equate the two, you see dxk is common, it will cancel out, and you'll be left now with dxi equals to gik dxi, which is simply what we have here. Similarly, Now let's try to work in the K prime reference frame. We know that in the K prime reference frame, our interval there will just be ds prime squared equals to some g prime mn. So we're just trying to use mn now, like other arbitrary um, variables representing I and k in that reference frame. So we have the xi, the x prime m, the x prime n here. But now we're working in the K prime reference frame. For this multiplication to be feasible, G prime mn must be a 4 by 4 matrix, dx prime m a 4 by 1 matrix, and dx prime n a 1 by 4 matrix, so that we can write out the components of this as dx prime naught, dx prime 1, dx2 prime 2, dx prime 3, and here we have dx prime 0, dx prime 1, dx prime 2, dx prime 3. So these are actually the components of the x prime m and the x prime n in that reference frame. So it's similar to what we have seen above, but just with the fact that they are prime. Now we can clearly adjust the last matrix to a transpose. So we can actually see that this can be written as the transpose of a column matrix. We have to understand that a row matrix is a transpose of a column matrix. So that's why we can simply change it to this transpose. The two rightmost matrices can be transformed to the unprimed using the Lorentz transformation equation. That is x prime I equals to alpha inverse ik xk. So this one is to transform from the k reference to the k prime reference. We have earlier seen this in the Lorentz matrix. So obviously we will take a differential of the both sides. You have the x prime I equals to alpha inverse ik xk. So we need to make use of this in the above expressions we have just determined. Using the Lorentz transformation, changing the I to m and n when necessary, which does not change the purpose of the matrix of the inverse matrix, we have ds prime squared equals to j prime mn, alpha inverse mk, dx0, dx1, dx2, dx3, and we have here the transpose of alpha inverse nk, dx0, dx1, dx2, dx3. Now we have to understand here that this relationship here is for dx prime n, while this other one here is for dx prime m. So we can see here that this Lorentz matrix here inverse is transforming dxm. So that's why we have mk. Why this Lorentz matrix here is transforming dx prime n. That's why we have alpha prime nk. So we are transforming, actually we are just trying to rewrite the primes in terms of the unprimed. So here we just need to do a little bit of simplification. So for this first bracket, last bracket here, we try to bring in the transpose. And whenever we bring in the transpose, we have the transpose of this times the transpose of this, but the terms will be interchanged. So actually this is what happens. So we have the transpose of this times the transpose of this. So you see that the positions have changed. Now I have to be careful with the term in the middle. The multiplication in the middle, these two matrices, is a scalar, hence can be placed anywhere. So you actually understood previously we were saying that this matrix was like a multiplication that will give you a scalar quantity. So it can be placed, you can place it at the end or in front. So we have placing right at the end, we have j prime mn, alpha inverse mk, alpha inverse nk transpose, and this. Now let's not forget that alpha inverse nk transpose is equal to alpha inverse nk, because the transpose of the inverse matrix is the matrix itself. It is a symmetric matrix, so its transpose is equal to its matrix. Now that implies that the s prime squared is equal to g prime mn alpha inverse mk alpha inverse nk dx0. So I've taken off the transpose here, so we have dx0, dx1, dx2, dx3, and dx0, dx1, dx2, dx3 transpose. Finally we have that ds prime squared is equal to g prime mn alpha inverse mk alpha inverse nk, and then this matrix here is dxm, and then this other matrix here that is to the transpose is dxn. So you actually see that they are not the same, because this one is a row matrix, this one is a column matrix. So that's why I have dxm and dx. Applying the invariance of interval postulate, that is ds prime squared must be equals to this, must be equals to this s squared. So we know that the interval must be the same with that of the other reference. So the interval in the on prime reference must be equal to the interval in the prime reference. So that's why we have to have this equated. So we can record that in the on prime we had this one jik dxi dxk, and we also had we have this for the primed. Now this dxm and dxn can conveniently cancel out dxi dxk because actually they are the same vectors minus of the variables, the script variables ik and mn. So you actually see that they cancel out and will be left with gik equals to g prime nn times the Lorentz inverse matrices. So that's the relationship between gik and j prime mn. Recall that the transformation between covariant and contravariant elementary elements is given by dxi equals to jik dxi, and we have here dxi equals to jik dxi. So we had seen that this gik matrix can be used to convert from contravariant to covariant and vice versa. That's why we have these two expressions given. So analogously, for the fourth tensor ai, we have ai equals to jik ak and ji equals to jik ak. So you can see that equation 1 is for transforming from contravariant to covariant, and equation 2 is from transforming from covariant to contravariant. And the Lorentz transformation matrix, we also remember the Lorentz transformation, which is alpha I equals to alpha ik a prime k. We call that equation 3. Substituting 3 in 1 for ak, so actually we can see that this is ai. We can see change it to k and substitute in equation 1. So we now have ai equals to jik alpha ik a prime k. So I've just simply substituted what we have on the left hand side, on the right hand side there in equation 1, and that gives us equation 4, and equation 2 is maintained. Now equation 2 remains. Now substitute 2 in 4. How? Where we have ak. Okay, let's see. Now substitute 2 in 4 for alpha prime a prime k gives ai equals to ji alpha I k jik a prime k. So actually you can see here that equation 2 is ai equals to jik ak. Now if we try to see something, if we put prime here, we put primes here, we have a prime I equals to jik a prime k, because we're just trying to convert between covariant and contravariant. So actually gik is not affected by the prime. Now we cannot take what we have had as prime and substitute over here as a prime k, and that's why you have this term here. You have this term gik a prime k in the place of a prime k, because we're making use of equation 2. Now we'll just let alpha tilde ik to be equal to gik alpha I gik. That's this matrix here in front of a prime k, and that will now imply that ai is equal to alpha prime ik a prime k. Now alpha tilde ik is equal to gik alpha ik gik, but we know the matrices. Actually gik is this matrix, alpha ik is this matrix, and gik is this other matrix. So if we do this matrix multiplication from left, we are going to result. So we'll result with gik alpha ik gik equals to this matrix, and we'll discover that this matrix is a inverse Lorentz matrix, which now implies that alpha tilde ik is equal to the inverse Lorentz matrix, that's alpha inverse ik. So using ai equals to alpha tilde ik a prime k, analogously dxi, so in the place of a we put dxi, and in the place of a prime k we put dx prime k. So we see that we can have this relationship. We had earlier seen that the elementary interval can be written as, so I also seen that the interval was dx squared equals to dx prime I dx prime l. So in the place of l, in the place of k, I put l equals to dxi dxl. Now using dxi equals to alpha tilde ik dx prime k and dxi equals to alpha I dx prime k. So these are the Lorentz transformation. To substitute in the above equation of the interval yields dx squared equal to alpha ti k dx prime k. So in the place of dx prime I, we substitute this, that's dxi here, we substitute this first equation, and in the place of dxl, we substitute this other equation, minus of the k, we simply change the k to l, and we substitute this other second equation in that place. So take note that the k has been replaced with l for consistency with the conical delta. We had earlier seen that we can write the equation as dx squared equals to, so we understand that we can change positions of alpha because we already know how we can change it. We can bring this dx prime k and dx prime l together. The notation don't change the fact that alpha ti k is equal to the inverse Lorentz matrix, and alpha il is the same as alpha ik, which we already know. All we just know is that l has been replaced, k has been replaced with l, but the matrix still remains the same. In linear algebra, we had learned that the product of a matrix and its inverse matrix is a unit matrix, which we then write as a conical delta. So we can clearly see that this one matrix here is the inverse Lorentz matrix, and this other matrix here is the Lorentz matrix, transformation matrix itself. So in order, if you multiply the two matrices, it should give you the unit matrix. So that's why we have alpha ti k times alpha il to be equal to this unit matrix, which we'll call now delta kl, which is the delta conical, and it's given by 1 where k equals to l. So you can see that on the leading diagonal where k is equals to l, you have a series of 1, while in the other spaces where k is different from l, like here, upper triangular, upper part of the diagonal and the lower diagonal, we have k different from l, we have zeros there. So that's what we call the conical delta.